Right. Hello and good evening everyone, and well done for getting here and not walking into the ice rink, because that's what I did. Any of you did that? No, just me? Okay, that's me. Lovely setting here too. It's a really nice environment, very Christmassy. I am Ted Stile, one of your committee members, accompanied tonight by Simon Hurst and Adrian Challoner, together with the R&G team, Daniel Ruby and Rayhan Hussain. Thanks for being here. Many thanks to those of you that submitted images for our astrophotography video. Keep them coming. So it's my pleasure to welcome you to this month's main lecture talk, which is titled "Seeing Jupiter's Aurora in a different new light." Oh, I've got a different title here. In a new light, which is a lovely title. That's quite Christmassy as well, actually. This talk will be delivered by our Royal Observatory astronomer, Dr. Ophelia Wibizono, who will enlighten us on that subject. As usual, there will be a Q&A which will be managed by Adrian Challoner at the end of the talk. Also, this lecture is being recorded and will be made available to the membership in a few days, with anything embarrassing I say edited out. So let me tell you about our speaker tonight. Dr. Ophelia Wibizono is currently an astronomy education officer at the Royal Observatory Greenwich. She has recently completed a PhD at UCL's Mullard Space Science Laboratory, using observations by space telescopes and spacecraft such as XMM Newton, the Hubble Space Telescope, and the Juno spacecraft to investigate how and why Jupiter produces intense X-ray aurorae. Her extensive science communication portfolio includes writing for NASA, performing at the Cheltenham Science Festival, and often interviewed on the TV news. Over the last 10 years, Ophelia has worked with organisations such as the Science Museum, the Royal Institution, and of course that observatory around the corner. What's its name? Just around the corner. She loves to communicate and engage science with all ages, including toddlers, lucky for us. So with that, please give a very warm welcome to Dr. Ophelia Wibizono.
All right. Thank you very much. Very happy to be here. And so I've been working at the observatory for the last 8 years, doing a few different jobs, but mostly presenting in the planetarium and the workshops for schools. And up to about, 2 weeks ago, I was also a PhD student, so very, very recently I've passed my PhD. And this is where I did my PhD, at the Mullard Space Science Laboratory. Even though it's part of UCL, we're based out in the Surrey Hills, near Dorking. So this is our building. My office was my office right there. We have a croquet lawn, a football pitch, a swimming pool, everything you need to study astronomy. As well as scientists, we also have engineers, so we actually build parts of spacecraft and instruments that go into space, such as bits of XMM Newton and the JWST as well. So we've already seen some pictures of the Earth's aurora taken by some of the members here. And this is just a video, and I mean, they're beautiful, aren't they? Breathtaking. And our ancestors have marveled at them for millennia. There is a set of cave paintings in the south of France, and they say that that could be the oldest recording of an auroral sighting, and they think it's about 30,000 years old. So we've looked at them for ages, and I bet they could never have imagined that the same phenomena happens many millions of kilometers away on other planets. But how do we get the aurora, or the northern and southern lights? Well, for the Earth, it all starts off with the sun. The sun releases a constant stream of charged particles called the solar wind, and this goes out to the edge of the solar system. And as it does so, it can meet obstacles along the way, like the Earth's magnetic field lines, and then they get deflected around and behind the planet because of the field lines. So we see here the Earth's field lines getting sort of pushed back, and the solar wind particles are dragged along with it. And then on the night side of the Earth, these field lines can get stretched, and then they can snap, and then they reconnect, and that shoots plasma or charged particles back our way, and then they enter the atmosphere. Once these charged particles enter the atmosphere, they can excite the gas molecules there. So here we've got some oxygen and nitrogen atoms or molecules. In comes a charged particle, exciting these molecules. Now, they don't like having this extra energy, so they spit it back out in the form of light. And different molecules need different amounts of energy to get excited, and so they release different kinds of light, or different colors of light, again in the form of different energies. And that's why the Earth has lots of different colors in its aurorae. So red comes from oxygen higher up in the atmosphere. Green also comes from oxygen gas, but found lower down in the atmosphere. And then the bluey, purpley color comes from the nitrogen gas. And you can see the aurora from space as well. So this was taken by astronauts on board the International Space Station. But I don't study the Earth's aurora. I studied Jupiter's, and Jupiter's was the first extraterrestrial aurora to be discovered. So back in 1979, the Einstein Observatory was observing Jupiter, and it found these emissions coming from the poles. And here we've got other planets with aurora, so Jupiter, Saturn, Uranus and Mars. Mars is the odd one out here because it's the only one that doesn't have a global magnetic field around it. We think in the past it used to, but when it's inside, it's kind of cooled, it lost its magnetism. But it does have very localized magnetism, sort of locked away in the rocks, and so you can get patchy and localized aurora there. And then this thing here at the bottom, that is not a planet, that is Ganymede. So Ganymede is the only moon that we know of that has its own global magnetic field, and the only one that has its own aurora. And something actually I find quite interesting about Uranus is that its spin axis and its magnetic axis aren't aligned, and it's actually quite hard to keep track of Uranus's north and south magnetic poles. And when we found it with Voyager in the sort of 70s, 80s, that was all good, and then we lost it for about a decade or so. And so the only way you can sort of know where Uranus's magnetic poles are by looking for the aurora. That just tells you where the poles are. And we detect these aurora in about a quarter of all observations so far. So Jupiter has the strongest magnetic field out of all the planets. So the bubble of magnetism around a planet is called a magnetosphere. And this is the Earth's in comparison to Jupiter's. So Jupiter's is huge. For example, its tail actually stretches out to the orbit of Saturn, 5 astronomical units away, and every 20 years or so, they overlap. So Saturn actually enters Jupiter's magnetosphere every 20 years. So the last time that happened was actually a couple of years ago, and we tried to look for X-ray aurora on Saturn. Spoiler alert, we didn't find it, and that's a bit of a mystery. And Jupiter, rather, mixing my planets up. Uranus also has Io. So Io, the most volcanic place in the whole solar system, has hundreds of active volcanoes on its surface. You can see one of those volcanoes erupting there. So they say if our moon had a similar sort of volcanic eruption on its surface, then we'd be able to see this through a pair of binoculars. They're that big. And so every second they release 1,000 kilograms of volcanic material out into the space around Jupiter and around Io. So you've actually got what's called an Io plasma torus, which is this ring of volcanic material around the orbit of Io. So Jupiter has a really strong magnetic field, and it's got this internal source of plasma coming from Io's volcanoes, and that's partly what my PhD was about. So the Earth's aurora comes from the solar wind. What about Jupiter's? Is it caused by Io, or is it caused by the sun? I'll talk a bit about later on. And this is actually a comparison of the two. So this picture is to scale. You can see how small the Earth is compared to Jupiter. You can fit the Earth inside Jupiter's northern lights there. And Jupiter's aurora are incredibly bright, about 1,000 times brighter than the Earth, and they're also permanent, so they're always there. And it's so powerful that if we can somehow harness that energy, it would have solved our energy crisis because it could power the whole of civilization. So these two are in ultraviolet, so we're looking at the UV aurora of Jupiter and the Earth. And actually, Jupiter's aurora comes in lots of different types of light. So radio waves, these comes from the electrons, so the negatively charged particles. When they get accelerated, when they travel along the field lines, they get accelerated and they also spiral, and that gives us radio waves, and you can detect radio emissions from Jupiter from the Earth, and that's partly because of these particles. The infrared aurora, so when these particles enter the atmosphere, they heat up the gas molecules in the atmosphere, giving us the infrared aurora. And you can actually observe them from the ground, so ground-based telescopes like Keck. You can detect the infrared aurora there. And then the visible aurora is actually the least impressive of Jupiter's aurora. It's very dim, easily lost in sunlight, so you can only detect them from the night side of Jupiter. So this picture was taken by the Galileo spacecraft. The ultraviolet aurora, probably the most studied of Jupiter's aurora. So this picture was taken by Juno as it sort of flew above the North Pole. But of course, we've also got the Hubble Space Telescope, who can also take images and videos of the UV aurora. So the UV aurora there is produced in a very similar way as the Earth's. The hydrogen molecules get excited by these incoming charged particles. But my focus, or the focus of my PhD, was on the X-ray aurora. So obviously, it's my favorite. And these are the telescopes that I used during my studies. So XMM Newton, it's the European Space Agency's flagship X-ray telescope, launched in 1999, and hopefully it's got a few more years left. I think it's funded until 2025. Yeah, it's really a workhorse of an X-ray telescope. I think it was only supposed to last for a few years, so to last 23 is pretty impressive. I also use the Hubble Space Telescope, so I use it to study the ultraviolet aurora, and we all know how great Hubble is. And Hisaki is a Japanese satellite, so it can actually monitor Jupiter over long periods of time, so over months. And not only that, it can actually look at the Io Plasmatoria, so that ring of volcanic material released by Io. And so we can see if Io's volcanoes have been particularly active recently, and that can help explain if Jupiter's aurora have been particularly bright recently as well. And yeah, I also used the data from the Juno spacecraft. So a great thing about Jupiter is that it's relatively nearby. We have sent other spacecraft there in the past. And so because we've got XMM Newton and Juno, we can they complement each other very well. So XMM does all the remote sensing stuff, so it detects these X-rays from far away, and then we've got Juno that's in situ, so it can actually take measurements of Jupiter's surroundings. It can take measurements of those particles and Jupiter's magnetic field as well. So the solar wind does play a part in Jupiter's aurora, even though it's really far away from the sun, it's about 5 times further away from the sun and the Earth, it does play a role. So just like the winds we get here on the Earth, sometimes they can be quite weak, other times you can get a great big gust of solar wind. So here, this is the ultraviolet aurora when we've got a weak solar wind. The ring is very dim, it's quite wide as well. And the polar emissions, so you don't get this at the Earth, actually, you don't get polar emissions at the Earth, but here, not a lot really going on. Whereas on the other side, when you've got a strong solar wind, that oval is now much brighter, and it's a lot more defined as well. And then the polar emissions, well, you can see lots of stuff going on there. You've got some spots, You've got some arcs forming here too, and that's very characteristic of a strong solar wind. And you might also notice that we've got some spots as well. So this spot here and this spot there as well. So those are actually caused by the Galilean moons. So as these moons go around Jupiter, they orbit Jupiter much lower than all these charged particles that's going around Jupiter, and so they cause disruptions. So a bit like how when you've got a boat in water, they sort of disturb the water, the same things happen here. And so they cause these features on Jupiter's northern light. So the Earth doesn't have this because, well, we don't have this internal source of plasma. The moon is relatively boring in comparison to the moons that Jupiter has. And I thought I'd just show you what Jupiter actually looks like in X-rays. So we've seen some, incredible photos from JWST, for example, and Hubble. But the X-ray image of Jupiter, well, looks like this. So these are the 4 telescopes that we have mostly used. The first one, Einstein Observatory. So in 1979, detected the first emissions or X-ray emissions from Jupiter. So you can see some blobs coming out of Jupiter there. And then in the mid-1990s, we had Rosat. The sort of darker the red, more X-rays we're getting there. So now we can clearly see that the northern lights are brighter than the south. But now we've also got some X-rays from Jupiter's equator as well. And that's because Jupiter's atmosphere acts like a mirror to solar X-rays. So these X-rays from the sun literally just bounces off Jupiter's atmosphere. And then also in 1999, the Chandra X-ray Observatory was also launched. So this is what its images look like. So Chandra is a NASA telescope, and it works very well with XMM. So XMM and Chandra complement each other very well. Chandra has a much higher spatial resolution, so it can pinpoint where these X-rays are coming from. So every point there is an X-ray photon. And again, so red is where you get more X-rays, blue is where you get not so many. So again, you can clearly see the 2 aurorae separated out by the disk. And because we can clearly see a circle here, this tells me that the sun was particularly active, and so it was releasing a lot of X-rays. And so all of those X-rays were bouncing off Jupiter. XMM Newton, on the other hand, doesn't take great images. It actually blurs its images, which is why, so the northern aurora here and the southern aurora, they seem to spill out over Jupiter's disk. So the green circle, that's Jupiter's disk. That's the northern lights, southern lights, and then the pink box there is the equator. But what XMM can do that Chandra can't is measure the energies of these X-rays. And that's very, very helpful to know what produces these X-rays, or what produces the aurora. Is it the sun, or is it ice volcanoes? So we've got 2 main types of X-ray emissions from Jupiter: the aurora at the poles, and also those scattered or reflected solar X-rays from Jupiter's disk. And this is just a video of the X-ray aurora there. So the X-ray aurora are actually fixed on Jupiter's frame. You can think of Jupiter as like a lighthouse or a pulsar. So as the planet spins, these X-ray aurora spin into an outer view. And this is just a graph or a plot of the X-ray aurora. So this is just for the north, but where it looks like it's getting brighter and dimmer, that's just the aurora rotating into view and an outer view, into view and outer view again. So during this particular observation, we saw the northern lights 3 times and a little bit there at the start and at the end. So that's another great thing actually about XMM Newton and Chandra, is that they can observe Jupiter for 30 to 40 hours at a time. So that's really great, because then we can compare the aurora from between different rotations as well. So you can see we've got a really bright flare here, and then the aurora next time isn't as bright. And actually, if I go back, if you look back at the plot, can you see how sometimes we get these pulses, these spikes? So sometimes the X-ray aurora pulse with periods of tens of minutes. So we call these quasi-periodic pulsations. So you get bright flares every sort of tens of minutes or so. And I think we're just starting to understand why Jupiter does that. And we think it's to do with waves. So you get waves in the magnetosphere. So the particular kinds of waves we're talking about here are the ones that travel along the field line. So you can think of them as like standing waves. So if you think of like a guitar string vibrating, it's the same sort of idea. So these field lines are vibrating, and that scatters the charged particles into the pole. So as these fields are vibrating, they've got a certain period, and so they scatter the electrons and the ions of the charged particles periodically, and then they enter the atmosphere periodically, and so we see these flashes periodically as well. So we think that's what's going on. And this is a neat example of how you can use in situ data, so data from Juno, which was measuring the magnetic field and also these particles, with remote sensing, so XMM mutants orbiting around the Earth, and then it detected these X-rays that Jupiter was emitting. So the great thing about the X-rays and about XMM mutant is that these X-rays from the poles, from the aurora, come in two different types. So you've got the low energy X-rays, which are the small green dots here. So those are produced by ions, so positively charged atoms or molecules, and they give off X-rays through something called ion charge exchange. So these ions, when they enter the atmosphere, they get close to a neutral hydrogen, and then it steals an electron from that hydrogen. And the captured electron is usually in an excited state, and that tells you how active the sun is. So the more sunspots you have, more active the sun is, more X-rays the sun gives out. And then the orange dots, those are how many X-rays essentially we're getting from Jupiter's equator. So we're not looking at the aurora, we're just looking at the equator. So you can see how the two matches up very nicely. And so the disk emissions from Jupiter are driven by the sun. Yeah, I mean, it wasn't surprising if you think about how they're produced, but it's quite nice to see it so clearly here. But you also get X-rays from other things around Jupiter. So Suzaku, the Suzaku satellite, actually has taken images of Jupiter's radiation belts in X-rays. So this is what we're looking at here. And you can also detect X-rays from at least 3 of the Galilean moons on Jupiter as well. So these are from fluorescence. So a solar photon comes in and knocks an electron from one of the, from the surface of the moons, and then gives us X-rays. And so we can use that to actually determine what the moons are made of, which is quite neat. So as well as Jupiter, I also studied Saturn for a bit. So I mentioned about, a couple of years ago when Saturn was inside Jupiter's magnetosphere, and we thought, oh, maybe this is going to tell us something new. Maybe we'll find the X-ray aurora on Saturn. Nope, we're still looking. So people have been looking for that for decades. So since we've known of Jupiter's X-ray aurora, people have been looking for X-ray aurora on Saturn. Haven't found it yet, but Saturn does give off X-rays through fluorescence. So the rings give off X-rays, and that's one of the ways that we know that you've got ice or water, frozen water in the rings. And again, Saturn's atmosphere also reflects or scatters solar X-rays as well. And then just last year, actually, we found X-rays from Uranus for the very first time. So I was very lucky to be part of that study. And this is the actual data. So each blue dot is an X-ray photon. Uranus is the red circle there, and what we actually did was split up the detector into Uranus-sized grids, and then we just counted out how many photons we get in each grid, and we found a grand total of 5 photons from Uranus. But that's enough to be a detection. They found 2 photons, X-ray photons from Pluto, and they said, oh, we found X-rays from Pluto, so 5 is more than 2. And when we actually calculated how bright the X-rays were from Uranus, we found it was brighter than we expected if Uranus was just scattering solar X-rays. So there must be another mechanism there that lets Uranus emit X-rays. And we don't know what that is. Maybe it's ring fluorescence, just like at Saturn. Maybe it's Aurora. And actually, I have 2 observations coming up with XMM, so in January and February, and hopefully we'll find more. So this observation was only about 8 hours long, whereas for XMM we've got about 100 hours of observations, so hopefully we'll detect more X-rays. And not only that, we've also got Hubble and JWST looking at Uranus at the same time. So we've got infrared, ultraviolet, and X-rays observations of Uranus coming up, which is very, very exciting, at least for me. And actually, the one other planet that has X-ray aurora is the Earth. So the Earth's X-ray aurora was discovered in the 1960s, and you can see it here. So whereas you've got ion charge exchange and electron beam styling at Jupiter, here we've only got electron beam styling. So the electrons are getting slowed down, and they give off X-rays. And this is one of my favorite accidental observations of the X-ray aurora on the Earth. So the integral satellite was looking at cosmic X-rays, so X-rays coming from black holes or wherever, and then the Earth just sort of wandered into view, and we can see the X-ray aurora there. So I think that's the North Pole there. So talking about X-rays from the Earth, so the SMILE mission is due to launch in 2024. So it's a joint mission by the European Space Agency and the Chinese Academy of Sciences. So the European lead is actually Graziella here, who was my supervisor. And what SMILE is going to do is it's got an X-ray imager, which is going to look for X-rays along this boundary between the Earth's magnetic field and the solar wind. And it's also going to look at the northern lights at the same time in ultraviolet. So if we can see how this boundary reacts to the solar wind, and then see what's going on with the northern lights, then we can sort of connect the two and see, what processes are happening there that's causing all of these particles to enter the atmosphere to give us the aurora. And we are hopefully, so NASA, one of NASA's objectives for the next decade or so is to send something to Uranus or Neptune or Neptune. And my team are trying to get an X-ray detector on that orbiter, because we've never had an X-ray detector on a spacecraft on the outer planets before. And so we're learning as much as we can about SMILE and its instruments and what it can do, and hopefully we can apply that to a Uranus orbiter, for example. So that's very exciting. And there are lots of other things out there in the universe that give off X-rays, such as active galactic nuclei, which is this. So at the heart of every big galaxy is a black hole or supermassive black hole, but not all of them are particularly active. So the one at the center of the Milky Way is quite, dormant. It's not doing much. There's not a lot of material around that black hole, so it's not eating so much. But this one here, I think this is Centaurus A. That black hole is actively, pulling material in. This material, it gets pulled into an accretion disk, and that's very hot, and that gives off all sorts of radiation, including X-rays, and sometimes they give off jets as well. And the same processes essentially is going on here as at Jupiter. So, you know, these X-rays are produced in a very similar way. But these objects are very, very far away from us. And at the moment, we can't send anything to these objects. And so studying Jupiter's X-rays and having Juno at Jupiter, we can maybe apply some of that knowledge to these, you know, more exotic places as well. And we're starting to detect aurora on brown dwarfs. Brown dwarfs is like that middle stage between planet and stars. So this is NASA's sort of representation of one. And we think, well, one of the things that a planet or an object needs to produce an aurora is a magnetic field. And we think magnetic fields are quite important for life. It protects, you know, life forms on that planet from their star's radiation. And so if we detect aurora on an exoplanet or wherever, or an exomoon, then we can study it a bit more. We can say, oh, you know, it must have a magnetic field of some kind. And then we can study its atmosphere more. We can study, you know, other things about it. And I don't know, maybe we can use that to find aliens. Maybe there are aliens out there looking up at their aurora, wondering, you know, if they're alone too. So yeah, that was quite a quick run through of Jupiter and its aurora. And yeah, thanks very much. I'll be happy to answer any questions.
Thank you very much, Ophelia. That was a very fascinating talk. I've got a question about one of the images you've shown on the Earth, which accidentally caught an X-ray aurora, didn't you? But it looks like it's not at the poles; it's at the side.
Yeah.
Why is that?
Oh yeah. So it's centered at the Earth's magnetic pole, not the geographic North Pole.
Oh, I see.
Yeah, so actually if you wanted to see the northern lights at the Earth, you don't want to be at the North Pole, you want to be further south.
Okay.
Yeah.
These are auroras you're finding it on different planets. Jupiter is very consistent. It's always it's always on these aurora shows. But the solar wind kicks it into more intensity, is it?
Yeah.
So, are you finding that base aurora on Saturn where there's no influence? What happens if they're isolated and no solar wind?
Yeah.
What would we see?
So for Jupiter, they'll always be there because it's got Io. Saturn.
Aurora chasers, take note. That's guaranteed. Cancel your trips to Iceland and Norway.
For Saturn, it's more like the Earth's actually. Yeah. It does have Enceladus, which does spill out material into its surroundings, but not to the same density as Io. And so, yeah, Saturn's is more solar wind driven than Jupiter's.
Right. Okay. So, and if you do find these phenomena on the other planets, that would suggest that it might be very common then on the other star systems.
Yeah. So Mercury is the only planet where we haven't found any kind of auroral emissions in our solar system.
Right.
So yeah, it's very common, and so yeah, must happen.
Good chances.
Yeah.
Right. Okay. Well, I'm going to hand over to Adrian Challoner, who will manage the Q&A with you.
Cool.
Thank you very much. First of all, congratulations on your PhD. Did you know Lucy Green at the Mullard?
Yeah.
It's beginning to feel like that we're an outcrop of the Mullard Space Science Laboratory, having had 2 consecutive lectures from there. Okay, I'm going to take questions from the floor. I will be repeating the questions into the microphone so that we capture them on the audio recording. So, I'll ask for questions. Okay, while people are thinking of questions, when is the SMILE probe going to launch?
So the SMILE probe, hopefully 2024.
Where does that launch from?
Oh, French Guiana, I think.
So it's on an ESA
Yes,
rocket?
it's on an ESA rocket, yeah.
Yep. And how long do scientists take to think up the names to get the acronyms like SMILE?
That is a good question, yeah, and yeah, Grazie gets asked that a lot. I think, I don't know how she came up with it. It's probably someone else, to be honest. And I think it's quite a nice acronym because not only does it, fit. It's the Solar Wind Magnetosphere Ionosphere Link Explorer. That's its long name. Yeah, you got it there actually. But the images that it's going to take actually does look like a smile. So this is the North Pole, South Pole, and it's this boundary here. So I think it's quite...
That's really cool. And at the Mullard Space Science Laboratory, you're designing some of the equipment that will be on that?
Yeah, I think they are. I think
Good.
so. Yeah, or at least building parts of it. But yeah, Grazie's the head of Smile.
So, do we have any questions yet? Yes, sir. Okay, so the question was about the two different types of aurora that you discovered, and did you know about those and go looking for them, or were they an effect that you found and then had to find an explanation?
So one of the open questions before I started was what caused the aurora, the sun or ice volcanoes? And I actually produced two models. So two like plasma population models. So one had all the stuff you'd find from the solar wind, and one that you'd find from ice volcanoes. And then I just sort of used those models to fit these spectra. And it wasn't until later on when I looked at them at the actual shape, it's like, oh, hang on, there's a pattern here. Maybe there's an easier way of actually determining what's going on just by eye, rather than creating these complicated models. Yeah. So yeah, it was just, it was a question that we knew we wanted to answer. Yeah.
Yes.
What instruments were used particularly in detecting the iogenic ions?
So the question was, what instruments were used for detecting the iogenic ions?
So XMM Newton has two main instruments on it, the X-ray telescopes. So this one is called the European Photon Imaging Camera. So it's just like a PN sort of detector, like a CCD. And it just measures the time that it detected the photons and also the energies, and then you can produce plots like this.
Yes, the front.
It never occurred to me to think about moons having So I was quite surprised. I don't know why, I just never thought of it. So can you tell us a little bit more about Ganymede's aurora? Because I think that's quite interesting.
So the question is about moons having aurora, something which we really didn't think was news to us. So can you talk to us a bit more about what happens on Ganymede?
Yeah, so you can see that the aurora here, they're quite near the equator compared to the planets. And that's because, Ganymede has its own magnetosphere, so its own bubble of magnetism around it. And that connects to Jupiter's magnetic fields. And these bits is where the two field lines sort of connect. So this tells us where the electrons and the particles are entering the atmosphere. And they are mostly produced by all the stuff that Io is giving out as well. Because it's bathed in all this radiation, basically, yeah.
So if we were stood on the equator at Ganymede, would we see aurora?
Possibly, yeah. The equator is pretty close to the equator, so yeah.
Yes. So the question is about the simultaneous observations that we've been making with different telescopes. And have you made any simultaneous observations with Io and Ganymede? Io and Jupiter, sorry.
Io and Jupiter's, yeah. So Hisaki, this satellite, so yeah, I did that using this satellite. So Hisaki can actually look at this Io Plasma Taurus and also the northern lights on Jupiter at the same time. And so you can see them brighten at the same time as well. So the brighter the Io Plasma Taurus is, the more active the volcanoes are because it's releasing more material. And then we can see how the northern lights on Jupiter respond to that. So we can't actually see Io itself, but we can see the Io Plasma Taurus, which is fed by the volcanoes from Io.
Do we have any more questions? Tej. In fact, Tej, I'll hand over the microphone to you. You can ask the final question, and then we can wrap up from there.
Okay, well, thank you very much, Adrian. And I do have one more question, because it's just occurred to me that Jupiter has, I think last count is 79 moons, right? So would the whole combination of the moon's mass, all 79 of them, and probably more out there, would that have an influence on the intensity of the X-ray aurora? And same with Saturn as well, I guess,
Yeah.
and other planets.
No, so it would just be Io in terms of, for Jupiter, because it's all the stuff that is chucking out into space that's causing the aurora most of the time.
Okay.
The other moons don't really play a part. Well, I guess the footprints. So these spots that we see, like this spot here, they can brighten or dim, but that's mostly due to what the solar wind is doing rather than what the moon is doing.
Right.
For Saturn, again, no, they wouldn't cause
They
so
won't
much,
have an
no,
influence.
no.
It's mainly the mass of the planet itself,
So yeah, so it's
atmospheric pressure.
atmospheric sort of
Yeah.
composition, strength of the magnetic field as well,
Right.
and the solar wind as well.
Okay.
Yeah.
All right. Well, that is the last question. Thank you very much, Ophelia. Thanks, everyone. Ophelia, Dr. Ophelia will be so now. Okay, let me just roll down my script here. Just bear with me a moment. And I'd already thanked you, Adrian. Right, so before we wrap up this evening's event, I would like to invite our great chair, Bobby Mano, who has a few words to say to all of us. Maybe something like, don't finish off the Kipling cakes before he's had some. We'll see. So please welcome Bobby Mano.
Thank you very much, Tej. And thanks again for that wonderful talk on Jupiter. And I know, ladies and gentlemen, this is our last talk for this calendar year. It's what we would call our Christmas lecture. And we have a wonderful venue. Do you all like this venue? And look at the view outside. And by the way, after drinks tonight, we're all going onto the ice rink, okay? And if you can take your drinks with us, we go to the drinks. But no, I'm sure some people may be thinking, Christmas lecture, we're talking about Jupiter. Has anybody mentioned that famous Christmas star? Was it Jupiter? Was it a comet? We're not going to talk about that Christmas star. Not in this astronomy society. And for those of you interested in history of astronomy, you may be wondering, okay, so Isaac Newton, was he really born on Christmas Day, the 25th of December? Some people say he has 2 birthdays, but if we get into that discussion, we're going to have to talk about the Julian calendar and the Gregorian calendar. So we are not talking about that either. I'm just here to say to all of our members, we are still defining our new normal, and we've heard this phrase, the new normal, several times over the past couple months. And I did mention that we've started live streaming together with our main lectures. This is the first session since the pandemic that we've not live streamed. And many of our committee members will tell you, sometimes members come up to us after these events and say, thank you very much for live streaming, because sometimes I pick up the kids and I don't have enough time to come down to the observatory, and live streaming works because it at least allows me to get the lectures and to view the lectures live and to ask questions and stuff. And as soon as we turn around, other members come up to us and say, you got to stop that live stream. Encourage people to come out more. We want to meet people. We want to meet and greet people a little bit more. So the thing is, as a committee, we are going to meet in January, and we are going to use evidence based on the last couple months and all of the recent events that we've had, and then make a decision as to whether we continue with the live stream or do it sometimes during the year. But I think what we can all agree on from all of the members is that we would like more opportunities to do just as what we've done tonight. Come out, meet each other, and socialize a bit more. And this is what we're going to keep in mind as we go forward into the new normal. Now, as we emerge from this pandemic, we've all had challenges. We've all had challenges at a personal level in many ways, many wide and varied ways. But as we settle in on whatever that new normal is, we should all remember, and this is one thing that we can take from the Christmas season, is that we can all remember to do just what we've had up there, smile, socialize a bit more. Let us all get together at every opportunity that presents itself to us and shake a hand, meet someone new. We have over what, Adrian, 450 members? 478 members? Let's meet as many as we can during these occasions, because I think this is what will help in overcoming all of the challenges that has been thrown at us from the pandemic and also from worldwide events. And this is what we are all going to have to go into the new year with. So on behalf of my wife Georgie and I, and all of the committee members, I would like to take this opportunity to wish all of our members and friends a very happy Christmas season. And we have a lot to be happy about despite all of the challenges. I mean, England is still in the World Cup, right? And for the new year, I would like to wish everyone the very best in facing whatever challenges that come our way. And as a society, we will do all that we can to move forward into the new year with that same spirit. So as we wrap up our session tonight, let's go downstairs. Please stay a while, have a drink, let's share some laughter, share some jokes at least tonight, right, Tej? So as we have jokes, I'm going to kick it off, right? So we had a German, a Canadian, and a Welshman walked into a bar. We're going for drinks just now, right? Now, normally this story would have an Englishman in it, but he's still at the World Cup. So I'll leave it there. Thank you all, ladies and gentlemen. It's lovely to see all of you. And please join us downstairs afterwards.
Thank you, Bobby. That was really nice, actually. In fact, this is a nice opportunity, Bobby, to reciprocate on behalf of everyone, to thank you for chairing this society since you took up the mantle and running things, including all the challenges with great finesse, Bobby. Thank you so much, and we feel very in assured hands with you. So, thank you, Bobby, again. That should put me back in his good books. Right, and lastly, before we enjoy the festivities courtesy of Clive Inglis and Brian Evans, we have upcoming events. As you can see, we are not done with this year yet. We have 3 more events squeezed in. So kind of get the feeling that we're making up for lost time during those wilderness years. There are 2 observing events, weather permitting. Do take advantage of Martin's generous invitation to his garden observatory under the excellent dark skies of Romney Marsh. He has an awesome 16-inch telescope, and he's a fantastic celestial tour guide, so do book for that. Places are very, very limited, mind you. We also have the Blackheath observing event. Do try to come to that, again, weather permitting. Yeah, the idiot that runs those events promises to make weather forecasts. He just promises to make better weather forecasts. Not naming names. He's easily embarrassed. But before all that, our next event is on Thursday. It's an astrophotography workshop. But as it's presented by Mike Maynell and Clive Inglis, I would call it a masterclass. Because you've seen their images at the beginning, right? Wow. So it's for anyone, whether you haven't done it before, or you want to improve on your astrophotography, or you're just curious to see how the magic works. So it's for everyone. Okay, a huge thank you to everyone involved in the hard work put into this evening's event, including my fellow Flamsteed colleagues and the RMG team. Thank you very much for that. And once again, Ophelia, on behalf of everyone here, thank you profusely for your generous time and your excellent talk for us. And thank you all for coming. Have a Merry Christmas and best wishes for the new year.